Hi, I'm Paul Inigeth. I'm the Sioux in the Phoenix Weather Office. This presentation is based on several published articles and a few presentations I've given over the past 5 years on the topic of atmospheric rivers, or ARs. We'll discuss what they are exactly, some of the mechanics on their formation, how El Nino plays a role, and look at a significant event that happened in Arizona. At the end, we'll highlight some of the forecast tools that are available for ARs. This tidal loop is of an AR hitting the Pacific Northwest, as depicted by the Integrated Water Vapor, or IWV. As you'll learn, IWV is not necessarily the best way for us to see ARs. So, what exactly is an atmospheric river? They are narrow regions appearing as filaments that occur outside the tropics, which appear to transport most of the water vapor to higher latitudes. They come in many different shapes and sizes and can be well over 1,000 kilometers long. When ARs impact land masses, they can bring substantial winds and rains, causing significant impacts, including property damage and loss of life. However, most ARs are weak and don't cause damage and instead bring beneficial rains. Locally, we may be familiar with the term Pineapple Express, and that is just an AR that appears to emanate from Hawaii. So briefly here, and I realize there's a lot of text on this slide, so you may want to pause and read through it a little bit, but really pay attention to the highlighted red words. And that goes for any slides through the rest of the presentation. If you need some time to digest them, by all means, please pause and take a look at them. So really briefly here, one of the first papers to do a thorough analysis of ARs and the notion that they are flowing rivers of moisture out of the tropics was Zhu and Newell in 1998. In an analysis of several years of moisture transport data, defined as the flux of specific humidity integrated from the surface up to 300 millibars. When isolating the atmospheric river component, they found several preferred regions of the globe for existence, including in the northeast Pacific Ocean. They associated these with the warm conveyor belts of synoptic systems and noted that they were responsible for moving a majority of water vapor across latitudes, despite occupying a rather small space. As we will see with later research, though, this isn't necessarily true. So why should you or I care about ARs? Well, big ones and or several successive ARs can cause a lot of problems. Several years ago, the USGS and various partners in California put together a document on the Arc storm, an extreme tail-end event that would really stress the resources of the state. This was used for planning purposes, kind of like the Great Shakeout for earthquakes. You can see from the bullets that a storm like the Arc storm would wreak havoc on California, with impacts felt for many months. The URL is included here if you'd like to check out the report. Interestingly, back in 1862, when California was just becoming a state, a very wet winter impacted California and caused mass flooding in the Sacramento and San Joaquin valleys. The Great Flood of 1862 resulted in water as deep as 10 feet in Sacramento itself. At one point, boats had to be used to get legislators out of what was then the state capitol. In Arizona, we've had our own brushes with significant ARs. In January 2010, a series of ARs moved through the state, resulting in widespread impacts, as seen in some of these photos. Significant rains, heavy winds, damaging winds. These storms had everything. Here's a loop of data from what eventually would become MRMS. The loop begins during the early morning hours of Monday, January 18th, 2010, and ends on the morning of Saturday, January 23rd, 2010. You'll see three distinct storms moving in off the Pacific Ocean and across Arizona. The strongest is clearly the last one. Just as the third storm moves in, you see some chaff dropped from our friends in the armed forces. As the storm intensifies and reaches a crescendo, several radars drop out. This was due to a telecoms outage. Note in southeast Arizona just how fast the precipitation is moving. We'll look at that in the next slide. Here's the velocity data during the height of the strongest third storm. Winds at 850 millibars were about 60 knots, and at 700 millibars were 80 knots. Based on the Tucson sound and climatology from SPC, both of these values would be near all-time record levels. Rainfall across the state was impressive, with some areas picking up over 10 inches. Across Phoenix, the average was nearly 3 inches, which is half of a typical year. Snow depth increased from just 1 to 2 feet along the Mogollon Rim and near 3 feet across the north rim of the Grand Canyon to widespread values of 4 feet plus. Flagstaff observed nearly 4.5 feet of snow during the 5 days, which was the third highest total recorded and about half of a typical year. Storm reports were widespread across Arizona, with snow in the north, heavy rain in the central strip, and much more wind issues in the south. Everything happened during these storms. The storm data estimate of damage was a likely conservative $11 million. So, all right, we should clearly care about ARs. Let's talk a little bit more on what exactly an AR is. Is it really a river of moisture-rich air moving through the atmosphere? First, we need to know how to find them. Generally, there are two ways. The first is to look at the total amount of water vapor from top to bottom, the integrated water vapor, or IWV. You know this as precipitable water. Satellites are actually quite good at detecting IWV over the oceans, but become less so over land due to signal degradation. To compensate, we use the method of noise in GPS data, but these details are outside the scope of this talk. So the idea is we see the water vapor as a plume. It appears as a river, and the assumption is that all that water vapor is flowing out of the tropics and into the extratropical areas. But studies that have done trajectory analysis have found that to largely be untrue. Rather, what we see on the satellite is the instantaneous position of water vapor, not the movement. As we'll see in the next few slides, the moisture, and eventually precipitation, isn't literally all these water vapor molecules traveling hundreds and hundreds of miles out of the equatorial areas. Instead, it's a combination of local convergence and evaporation that are generating the appearance of ARs. Now, that isn't to say the water vapor doesn't travel from the tropics northwards. It does, but at much higher altitudes. So should we look at IWV? No, we want to look at the flux of water vapor, sometimes called integrated water vapor transport, IVT, or moisture flux, MF. Here, if we look at the correlation between precipitation and moisture flux, which is on the left, versus precipitation in the middle, clearly moisture flux is better correlated across the west, as shown in the difference panel to the right. Depending on the researcher, the tool you're looking at, or your own procedures, moisture flux is simply the wind speed times the specific humidity integrated from the surface to some higher level. Some researchers use 700 millibars, some 500 millibars, and others 300 millibars. Really, the amount of moisture above 7 to 500 millibars rapidly becomes small, but any of them will generally suffice. Let's look at the idea that these are rivers of moisture moving through the atmosphere. We'll do that by looking at different parts of a water budget applied to a single storm. These 6 figures show the different components in a system relative coordinate. The black lines are the positions of fronts. The top left is total precipitation. The top middle is evaporation. Top right is the rate of change of water vapor. So red means water vapor is decreasing, blue increasing. Bottom left is total moisture flux convergence, where blue is divergent moisture and red convergent moisture. The bottom middle and bottom right are mass convergence and advection. So what do these mean? Well, some are no surprises. Precip falls along and ahead of the fronts. Moisture divergence happens behind the cold front, convergence ahead of it. Mass divergence behind the cold front causes mechanical lifting, along and ahead of the front, and precipitation. But some interesting stuff does show up. There's a lot of evaporation behind the cold front. Despite the post-front evaporation, negative advection of water vapor occurs behind the cold front as the system relative winds advect relatively dry air behind the cold front cyclonically. Positive advection of water vapor occurs ahead of the cold front as the cold front sweeps high water vapor content into this region. The magnitude and extent of the negative water vapor advection region exceeds that of the positive water vapor advection region. This imbalance results in moisture accumulating along the cold frontal boundary. Here's the main point. The relative motion of the cold front acts to form and maintain the filament and appearance of the AR parallel to the cold front as the cyclone moves poleward. What is going on is a constant sweeping of existing moisture, ingestion of new moisture through evaporation, and deposition by rainfall. Here's another way of looking at it. We have 2 diagrams here of the same storm we were just looking at. On the left is the water vapor transport with winds relative to Earth, just like you might see in A-Ellipse or online. And on the right is moisture transport relative to the storm itself. You can see from the wind field that the cyclone really is a wave moving along in the flow. You get the sense of a sweeping up of moisture. As the cyclone travels with a speed and direction that is comparable to the wind speed and direction ahead of the cold front, the along front component of the system relative IVT in this region is small, and hence the water vapor flux towards the cyclone center is also small. Closer to the cyclone's warm front, the system relative winds gain an along front component, splitting into a cyclonic and anticyclonic branch as the airflow rises up over the warm front. That's the warm conveyor belt. Thus, in the region, the warm conveyor belt airflow transports water vapor cyclonically into the cloud head and anticyclonically into the cloud shield. The reduced along front transport and storm-centric framework does not mean there's no poleward transport of water vapor by the cyclone, but that there is little poleward of transport of water vapor into the cyclone itself. Thus, instead of poleward transport occurring because of a direct and continuous feed of moist air from the subtropics to the extratropics, as suggested by the term atmospheric river, poleward transport is the result of a continuous cycling of moisture within the cyclone itself. Local convergence of moisture occurring ahead of the cold front provides a source of moisture at the base of the warm conveyor belt airflow, which ascends into a slantwise motion, reaching saturation and forms precipitation. Subsequent convergence of moisture results in a continuous cycle. Thus, the saturated air is formed by the cyclone and moves with the cyclone, leaving behind a footprint of where the cyclone has been as the cyclone travels poleward. Let's switch gears to another recent paper that assesses ARs and how various factors may change them. In this study, the authors built a database of atmospheric rivers across the North Pacific based on roughly 30 years of reanalysis data. They did this by using a coast-centric domain, which you see in the A panel, to obtain when ARs hit the west coast. They reoriented that into the B panel. And then you get how much precip was there and what the peak moisture flux was, and that's the C panel. Note the quote here, which is in line with the paper we were just discussing, though this one was published before. ARs are pathways for moisture, recycling the moisture between the ocean and the atmosphere. In total, the authors of this paper identified nearly 5,000 ARs. A lot of them are weaker, and so to get a more robust signal, they focused on the 85th percentile events. So that would be to the right of the vertical gray line. This subset of higher-end ARs resulted in 749 events. Here are the 749 events composited based on the ENSO mode. The biggest impact ENSO appears to have is shifting the jet position north or south, which impacts where the Rossby wave breaking region is. You see the jet anomalies, which are the dark gray lines, are shifted south and more intense during an El Niño, while the moisture flux anomalies are spread out much further south. The PV anomalies are also considerably weaker, possibly indicating less intense breaking. While Rossby wave breaking is a really interesting subject, I'm not going to cover the fine details of it here, partially because I'm just learning a lot more about it myself. So here's a similar analysis, but using the MJO phase. Phase 7 has a very robust signal, though Phase 2 spreads moisture flux anomalies well south into the Baja. If we look at the 749 events, but stratify based on month, this is what we get. The top row is climatology. The middle row is the 749 events, and the bottom row is an even smaller subset, which turns out to be 112 of the most intense ARs. We see an evolution of the jet stream, which is the red contour, shifting further and further south, and anticyclonic Rossby wave breaking intensifying, which is the PVU, the dark gray lines, indicating the potential for more undercutting as the winter wears on. The Northeast Pacific low intensifies too, which is the light gray lines. If we look at where those most intense 112 ARs come from, we get this map. The back trajectories are shown here, color-coded, based on peak moisture flux intensity. You'll note that the lower intensity ARs, which are in blue, are generally to the right, and the higher intensity ARs, which are red, extend well back into the Pacific. The plot to the right verifies this. If you plot intensity versus latitude, You see the most robust ARs get their start in the Northwest Pacific. This is a solid endorsement of why it is always important to take a broad look at the synoptic pattern. In this 4-panel, we can see how those 112 events on average unfold as they make their way across the Pacific. First, in the top left, there's a strong jet and associated baroclinic zone stretching across the North Pacific, fairly zonal at this time. Next, in the bottom left, the jet pushes further east as the surface low, which is the light gray, to the north intensifies. You can begin to see an undulation in the PVU contours, which are the dark gray. As the AR nears the coast, in the top right panel, it takes on a sharper north-south orientation as the Rossby wave begins to break and the jet streak curves anticyclonically. Finally, at landfall, which is in the bottom right, the Rossby wave appears to break and the jet breaks and retracts. Note that the moisture flux is at peak strength while it is offshore. Okay, we've talked about IVT or moisture flux a bunch already. What should you be watching for? In general, and I've observed this, albeit subjectively myself, a value of 250 kilograms per meters per second is a good discriminator between not strong enough to precipitate and could cause some precipitation. It isn't a hard or fast rule and is open to more research if you're interested, but it's a decent starting point. So let's go back to just show how big of a deal ARs in the western US are. This map shows the percent of cool season precip on the left and snow on the right that are attributable to ARs. In the Pacific Northwest, it is over 2/3. Even in parts of southern Arizona, it approaches 50%. Another selling point on the importance of monitoring and forecasting ARs. This map shows the AR fraction. It's what part of the cool season precip can be attributed to atmospheric rivers. You see that it's a very high portion, mainly in the southwest, from the Sierra down towards Southern California and into most of Arizona. But you do see some pretty high values moving up even into Utah and western Colorado. This map depicts when they're most common. In the southwest, most common time is December and January. Here we see the typical duration for an atmospheric river. The highest values are clearly up in the Pacific Northwest, where a typical AR lasts for about 24 hours. And you see a pretty considerable extension going well into Montana. There's another area of higher values down in the south in Southern California that kind of moves into Arizona. And you can see the blocking that takes place basically from the Sierra Nevada as that shadow falls into Nevada and parts of Utah. If we look at the correlation of AR precip with El Niño, we see it is quite high in the southwest. The connection is much weaker with the PDO. Continuing with the El Niño theme, some very recent work was done to look at just how does El Niño change precip patterns. While this research was specifically geared at ARs, it is tangentially and timely for us. The researchers used various data to force 3 models and generate a 130-member ensemble. Here are cumulative probability distribution functions for precipitation in northern, central, and southern California from top, middle, and bottom. Compare the climatology, which are the green lines, to strong El Niño events, which is in red. The distribution is strongly shifted to the right. In Southern California, they found just a 10% chance of below average precipitation during a strong El Niño, with a 50% probability associated with over 150% of the climatology. The precipitation does not come suddenly and all at once during the strong El Niño events. The signal doesn't become very robust until January and then continues into April. So there is a delay. When it doesn't start raining in October or even early December, that doesn't mean a bust is underway. Patience is needed. Likewise, the number of precipitation days increases as you go further into the season. But does a strong El Niño mean more storms or more intense storms or fewer but really powerful storms? Based on the research, it really looks like just more storms. Here's the change of precipitation on days when it rained. None. So more storms of similar intensity, which means more ARs, or at least more opportunities for rain. So with this knowledge we have now, let's review a paper that did a really thorough job of breaking down that big AR event, which impacted Arizona in January 2010 that we saw earlier. This 4 panel shows the progression of 3 ARs as they moved into Arizona. The shading represents moisture flux, the blue lines are moisture flux standardized anomalies, and arrows are moisture flux vectors. The 3 ARs are labeled, with the third being the most powerful. IVT values exceeded 1,200 kilograms per meters per second. Also note how the ARs didn't have any apparent direct tropical connection, and consider that in light of our previous discussion on if these are actual rivers or not. This 4 panel is valid at 12Z on the 21st of January 2010, just as the strongest AR was approaching Arizona. The top left is the moisture flux. The AR position and orientation is pretty evident. The top right is 850 millibar height, specific humidity, and wind. The bottom left is 850 millibar potential temperature, frontogenesis, and winds. Note the frontogenesis on the tail end of the AR, indicating a strengthening baroclinic zone, enhancing mass convergence, and ultimately a stronger AR. The bottom right is surface latent heat. Note the large area behind the cold front, just like we were previously looking at. Here are a few more variables. The freezing level in the top left, you can see the increased values in and ahead of the AR. In the top right, you have the 500 millibar height, vorticity, winds, and normalized height anomalies, so a fairly strong shortwave coming in. Lots of PVA in the system, clearly strengthening. And the bottom left, you have the jet streak, and you can see how that's undulating. There are peak values near about 200 knots. So let's take a look at a cross section to see what else is going on. It'll be for that black line that is just off the California coast. Here we have from northwest on the left to southeast on the right. In the top left are the winds, you see that in the barbs, and then we also have the along AR component of the wind speed in red. Potential vorticity is shaded, and the potential temperature in black contours. We see that strong PV anomaly on the poleward side and on the extension of the potential vorticity extending south and lowering in height along the polar front. If we look at the omega in the bottom left panel, we see the ascent is strongest relative to the jet dynamics and also in the core of the low-level AR, which we can see better in the bottom right panel where we are depicting moisture flux. So let's jump ahead 12 hours. The AR has intensified based on the moisture flux values. Looking at the other values, the higher freezing levels are now over Arizona. The trough is taking a negative tilt as it approaches the Baja Peninsula, and the jet streak is showing a deeper dip as it weakens slightly. So let's take a look at one more cross section for that black line extending from Northern California into northern Mexico. In the top left, the along AR winds, those red contours, have weakened a bit, and we see the PV isn't undercutting the jet as much anymore. However, looking at the position of the jet in the top left and the now stronger AR in the bottom right panel, based on the moisture flux, we see they are now better aligned. This results in much stronger and deeper ascent, which is shown in the bottom left panel. You've got ascent from the surface to the tropopause. These images show the importance of getting all the pieces lined up just right to really maximize the potential of any system. So the question continually comes up of, is this a river of air, or is it really juicy air coming up from the top tropics? As we've seen, sometimes yes, but most often no. The moisture is in place and simply swept up by the system as it passes. This interesting analysis shows back trajectories of air parcels released at 1, 2, and 3 kilometers above the ground. The 1 kilometer is light gray, 2 kilometers are colored, and 3 kilometers are dark gray. And they're released at the white dots on the 21st of January 2010. You'll note that basically all the trajectories arc back to the north of Hawaii and show a genesis of somewhere in the central Pacific. The different colored trajectories released at 2 kilometers are from different latitudes, blue in the north, green in the middle, and red in the south. Note that the southernmost parcels actually started at the highest elevation above 700 millibars. As the parcels descend, they pick up moisture but never really saturated. The parcels further north were the only ones that reached higher saturation and exhibited ascent near the end of their journey. If we do a back trajectory for parcels originating over Phoenix at the height of the storm, and we release them at 1, 2, and 3 kilometers MSL, 1 kilometer red, 2 kilometers black, and 3 kilometers blue, we get this trace. The lower two parcels started their journey at the surface, southwest of the Baja Spur, really not that far away. The highest air parcel came from the furthest away, and again exhibited downward vertical motion before rising drastically at the end as it was caught in the broad scale lift. The authors presented this idealized conceptual model of what happened during the strongest part of the storm. The fact that the AR was able to shoot the gap of the Baja Peninsula played a big part in the amount of precipitation it brought, and we'll see that qualified in what is part 2 of this paper. This cross-section schematic on the right shows an idealized flow of an AR undergoing orographic lift as it flows perpendicular to the Magellan Rim. The warm, moist air is lifted into cooler air, which causes the rapid condensation and precipitation. Okay, so enough with the research at this point. What about forecasting these things? Luckily, we have several tools at our disposal that can help. The first I'll highlight is this tool from Western Region, which displays the IVT from both the GFS and the GEFS. You can access it from the URL in the top left or from the Western Region Confidence Toolkit. From the graphics type drop-down menu, pick GEFS/GFS IVT. The 250 kilogram per meter per second contour is highlighted in red for easier interpretation. Next is the situational awareness table. That's available through the Western Region Toolkit, or you can use the URL in the top left corner. The far right column is integrated water vapor transport. So for this tool, I suggest using North America for the plot region and Southwest for the table, and then selecting the NAIFS percentile for the output. And we want to use percentiles because a lot of these parameters are asymmetrically distributed, including IVT. So the graphics will display the NAIFS data, which is again in the ensemble from the GFS and the Canadian, and color shade the percentile values relative to a 3-week climate window centered on today. So this will tell you if these values are unusual or not. The next several slides will highlight the atmospheric river portal from Plymouth State University. The URL is in the top left and is also in the Confidence Toolkit. First up is the IVT from the GFS, similar to what we just saw, but available on this site. Next is the time-integrated IVT. The idea here is that the longer the duration of high IVT values, the more significant the precipitation. You can choose values ranging from 1 to 7 days. Here's a recent example of what IVT looks like for 1, 2, and 3 days. This event resulted in widespread flooding and impacts across western Washington and Oregon. The next graphic shows the probability of IVT exceeding 250 kilograms per meters per second. Just pick your forecast time from the links on the right side. Recently added by the developers at our request, you can select a 7-day meteogram for numerous points across the West. Just find the dot you want on the map to the left, click on it, then click on the little link that pops up. The image to the far right will update, depicting moisture flux and the height of the 0-degree isotherm. You also get 6-hourly precip and IWV/IVT values. The images in the middle is the moisture flux for a selected time from the links above. This is a pretty interesting graphic here. I'm showing a loop here of forecast over about a 2-week period, so it doesn't make sense now, but give me a minute. So the map on the right side has a bunch of dots along the west coast. Each one of those dots is for a latitude, starting at 50 north and going to 32 north. Each dot represents a row on the graphic to the left, so that is the y-axis. The x-axis is time, with now on the right and the forecast days to the left. So +5 means the day 5 forecast, 5 days from now. +10 is 10 days from now, the 10-day forecast, and so on. Each grid you see is then the probability from the guests that the point along the coast at that forecast time is greater than 250 kilograms per meters per second. So we're looking at, in essence, the probability of an AR landfall. Now the loop I'm showing is for 2 weeks of forecast for an event in January 2015. As you watch the loop, you'll notice around the forecast made on Monday, January 26, 2015, some relatively high values show up out around the days +10 to +14 range. Yellows and oranges indicating about a 50% chance of 250 kilograms meters per second or higher. As later forecasts come in, you can almost see the AR as it approaches the coast. That is, it gets closer and closes in the forecast. You also see the probability increase to about 100%, widespread purple, even when it was still 7 to 10 days out. This is a pretty good example that even though numerical prediction is by no means perfect, we can be getting some actionable information out to a full 2 weeks even to use when communicating to our customers. Here are the references that I've used through this presentation. If you'd like some more information, there is also an Esrael site you can go to get that. And if you'd like some further information, there is a comment module available on satellite feature identification for atmospheric rivers. It's about 75 minutes, and you can view it at the URL there. Otherwise, thank you for your time, and I appreciate you listening. If you have any questions or feedback, by all means, please send me an email.